Hello, everyone, again. I think we can start. My name is Sofia, and our guest today is Sergey Sidorov, software engineer at Meta. Today, we will discuss why overload happens and how to deal with it in real world systems. So, let's get started. Sergey, please, the mic is yours.
Yeah, thanks, Sophia. Super excited to be here. Thanks for inviting me, and super excited to see people joining the chat. So we have quite a lot of them. So pretty cool. I hope this session will be useful, and so let's get started. So overload readiness. Let's basically set the frame for what we're going to talk about in general, right? What is sort of like overload? What do we actually mean here? So in today's world, expectations for software is pretty high. We use countless apps every day, and also we see that there are plenty of alternatives for every app that we use, which means that the quality, like speed and reliability of the services, decides who keeps using them, right? Who wins? And one of the biggest churn that drives users away from the platforms is reliability gaps, often caused by overloads. So we will explore why overload happens, how local spies can turn into the cascading outages, and what actually helped systems to stay resilient under stress. So just a quick slide about myself. I'm a software engineer working on reliability infrastructure at Meta. I build systems and libraries that are backbone for the company service to basically to remain running up and stay healthy. Also, it helps engineering teams to be productive with safely rolling out changes to production. So I have a quick email here. So if you have a quick question or want to get a copy of the slides, just drop me a message. And we can chat. So to the next slide, why should we care about overload in the first place? So overload has been a top trigger of outages and reliability breaches for many years. This is quite significant. Another one is blast radius is huge. So if overload happens, it usually impacts many customers all at once, signifying the impact of an issue. And last but not least, it's very hard to recover from overload event once it happens. Bringing additional capacity in this case can be too lengthy and not always helps. But given the problem is so popular, is there any solution to that one? Is it like a solved problem? Unfortunately, it's not. Here's just a quick slide showing a teeny slice of publicly available data about overload-related incidents across industry. You can see that popular companies, like you probably heard about, they have overload-related incidents quite often. Every quarter we can see, and this is like a very teeny proportion of those. As you can imagine, companies lose millions of dollars because of those outages. So it's sort of like clear that reliability and overload protection is pretty huge topic to talk through in depth during 1 hour. So I tried to put together high-level ideas and concepts that we can apply when thinking about system overload. And I would expect most of the concepts that we're going to talk through will be familiar for engineers working with reliability engineering and have reliability engineering background. But if the concepts are new, you will definitely find this talk useful. Also, feel free to drop your questions in the chat. I will try to budget 10 or 15 minutes at the end of the session to answer them. Just to set the context, I thought it would be too boring if we just talk about theory and giving it basically, I'm not representing any company or particular product. I come up with a virtual example where I can show how those overload protection mechanisms apply in practice. So meet New Social. So New Social is just a brand new social media app which has all of the familiar features like story sharing, post reactions, and so forth and so forth. So currently New Social has thousands of users and backend handles about hundreds of QPS. queries per second during peaks. We anticipate significant traffic growth in several months because of the upcoming celebrity concert. And we expect many users will live share their experiences during this time. So Olivia is an engineer working on new social. She ensures that new social app is fast and stable. She knows about upcoming event and decides to proactively test if the new social can handle the increase in traffic. So the application architecture is a classic client-server design. Olivia sets up a testing environment to generate artificial traffic to the app servers and observe system behavior. Olivia wants to be very specific about what we're going to test and what do we mean about overload. So we bring terminology up front. And so we have three things that we're going to touch most of the time during today's talk: throughput, goodput, and overload. So what these things mean and how they relate to each other. So throughput is essentially the total number of requests per second that is being sent to the server at any given point in time. So essentially, this is the traffic that is being generated and that our backend systems receive. The goodput, though, is a subset of the traffic of this throughput that is handled without errors and with low enough latency for the client. So it's basically something that client is useful for the client. Let's say you send a request and you wait for too long, right? So probably this is not useful for you because you probably retry and like refresh in the app, right? So the first one will be definitely not useful. It won't be counted in the goodput, right? So I hope this makes it clear. An overload is basically a scenario when the demand for the system resources exceeds capacity. In other words, the goodput doesn't grow with the growth of the throughput. So Olivia start measuring throughput and goodput in her testing setup and basically printing those the results on the chart. And yeah, basically we have this like very simple chart where we have request rate our systems can handle is the x-axis, and y-axis is actually useful work being done. So we start sending a few tens of requests per second and record how many of those successfully return. So far so good. We just add a little bit more and still expect retries. So we see like 100 requests being sent from users, 100 of them successfully handled with low enough latency. But then around 100 requests, the goodput stopped growing. Olivia actually expected that. She thinks if our server capacity is around 100 requests per second and server cannot handle more, we probably just remain at 100 line. Because this is what we want, right? So just as whenever we reach the maximum possible request rate at given capacity, adding more capacity would be the solution, right? In that case, but this server will just continue handling this 100 request. But reality is not that simple, unfortunately. She was very surprised to see that shortly after server capacity was reached, the goodput dropped significantly. And even more mysterious, the goodput dropped right to zero, and server became totally unresponsive and unavailable. At this point, we lost the entire traffic, and no one is able to use the app. Basically, this slide shows Olivia experiments. The goodput essentially dropped back to zero, which means nothing is being processed. And on the right side of the slide, you can see the availability chart at the time. So at some point, we just lost the server rapidly. This is typically what happens in the real world. So Olivia decides to dig into the problem and discovers that it's actually quite expected and actually quite common behavior. So in reality, without proper overload protection, the graph, as I mentioned, would look very similar to the previous slide. The growth in throughput could easily lead to server collapse. when the quantity of useful work a system accomplished decrease substantially, the number of requests may go up, but server crash and accomplish even less work. So even less than before the new traffic arrived. So server may become totally unresponsive. And this is basically what is called overload. So if we look deep into this problem, we can see that it happens because once server capacity is reached, adding more work to it will just make server to share resources among a larger number of tasks. Eventually, every task is going to get only a little fraction of the resources, and basically it will be not enough for this task to complete in foreseeable future. So imagine you have like more and more work being added to the task queue, which is a sort of like quite a vague description of how any server and any operating system would handle this. So we have multiple CPUs, like actual things that execute instructions in computer, and they have multiple tasks, which can be like a user request, right? Threads, and we try to execute this task on this multiple CPUs, but at some point, if the number of tasks getting too large, we just starting to give just a teeny fraction of these resources to every task. And the task completion time directly depends on what is the fraction of the resource that it's given. So at some point, tasks won't be able to finish within reasonable time, right? It will be just taking too long for the task to finish, which equivalent to nothing is being done, right? So how to avoid this problem is essentially by introducing a load shedding. So basically, the solution is avoid adding more work to the server that is already running at hot, right, at or more at above the capacity. So this mechanism essentially ensures that we can sustain the load when new traffic arrives. So there are many different strategies how load shedding can be implemented, and typically the queue timeout approach is used. What is that? When task arrives, like a user request, it basically sits in the queue. And if it sits in the queue too long, server can proactively reject it by sending client a special type of response. This response indicates that server cannot handle this task currently and ask it to retry later. Optionally, it can include a special time marker, basically signaling when the server will be less loaded and retry would be feasible. Some of the popular solutions in industry include Hey Proxy with the maxcon, maxq parameters, Nginx, quite popular and widely deployed solution for that as well. So it has limit connections and limit request parameters, and Thrift communication framework, RPC framework, using queue timeouts, the technique that we just illustrated on the previous slide. So Olivia decided, okay, this is a pretty good thing to use. She introduced this concept into the server code, and results are much better this time around. She still was surprised to see that even after adding load shedding, the good put is inevitably decline, even though this time server had much more runaway before it get unavailable, around like 130 throughput RPS. So, but this is still a result, right? Because we have this larger flat line, meaning that server can handle something, right, and remain at the good put of about like 130 with the scale of the throughput, giving us more time to actually auto scale and add more resources, right? Because in previous example, in previous scenario, we just dropped very rapidly, so we don't even have time to add resources. So Olivia learned that auto scaling is not enough alone, right? And server should be able to protect itself. It should have mechanisms built in to protect itself. So this is the lesson number one. So Given that results are not impressive yet, Olivia decided to figure out why output declined at around 200 QPS. And she basically looks at another important metric, which is traffic amplification. And she noticed that somehow after server reaches capacity, traffic starts to go, basically to grow very fast, almost exponentially. She found that once server reaches a capacity, it gets slower, and clients start to retry their requests. That is expected, right? So if I try to update my feed in the social app, and it takes too long to render, I would probably just retry. So Olivia decides to plot original requests and retries separately, and notice that retries significantly amplify the traffic at some point. And this confirmed the hypothesis about retries causing significant traffic amplification, and those retries making server receive even more work when it's running hot. She knows retries are important and any system needs it, but they should be handled carefully to avoid retry storms. And here comes retry budgets and circuit breakers. So let's talk about this a little bit more. Olivia looks at the client code of our new social app. This code is probably in the mobile app or in the front-end app. It doesn't really matter that much. And she finds a very typical exponential backoff logic for retries. Client is trying to make a request call. If request fails, it retries later. Time between retries grows exponentially. I mean, the rationale is pretty straightforward here. If request didn't succeed recently, and if you retry it immediately, it won't succeed either, most likely. So basically, if you have continuous unsuccessful attempts in the past, so probably it doesn't make sense to retry right now, but wait a little bit and give server more time to recover and retry later. So Olivia discussed this problem with Lucy, another engineer on the team at New Social, and they explained that exponential backoff alone doesn't eliminate the load amplification. It merely delays it because of the exponential growth in the delayed in the retries, right? But at some point, downtime threshold exceptional backoff becomes like ineffective, right, in reducing the server load. Lucy mentioned that clients should avoid sending the request in the first place if it knows that server is running hot. They recommended Olivia to experiment by adding circuit breakers to retry logic. And circuit breaker is essentially a mechanism to prevent sending requests when we know that it likely won't succeed. So this is just a simple diagram illustrating the logic of the simplest possible circuit breaker solution. So it has three states: closed, open, and half open. This is quite similar in electrical engineering. For example, in your flat, you can find the circuit breakers that actually switch on and off the power for a particular area of your apartment. And it works quite similar in principle. So here's the same thing. Closed means that basically if we have we allow requests to sort of go through, right? We allow requests to reach the server. At some point, if we have too many failures and we reach the threshold, they open the circuit breaker, right? And at this point, nothing goes through, right? So if client tries to reload the feed, send more requests, we just don't send it, right? We just know, we're not locally on the client side, we know that there is no point in sending requests. So we remain like that until some point in future, when we try to sending the request to the client again. And this is called half open. So why half open? Why do we need this state? Is basically, so imagine if you open it immediately, right? So it's just a binary, right? You enable and disable, like a switch. In that case, once you enable it, right, you start sending all of the traffic right away. At this point in time, server might be still recovering. It might be not ready to accept the entire traffic, right? And you can end up bringing the server down again and again, right? So to avoid this scenario, we start slow. We send just a teeny fraction of the request first. This is called half open. And then once we see that actually most of the requests that I send are successful, I can go to open, right? Sorry, I can go to closed and basically send the entire traffic to server. Nothing is getting throttled. So Olivia decided to introduce this thing to the client and rerun the load test, essentially. And results are much better this time around. The server handles traffic, and there is no sign of degradation. Obviously, at some point, it will reach the brownout when server basically spends most of the time rejecting requests. But that steady runaway that we have when good put remains flat is just enough for us to just enough time for us to auto scale, right? And obviously, this is how the chart would look like for any system, right? So it's impossible to achieve the flat line that is going to be flat, like, for any throughput. At some point we definitely like reach the physical limitation of the machines and the resources. But the most important thing for us here is how long we can actually sustain the good good put, right? Sorry for that tautology, but essentially, yeah, we need to have larger time for us to add more machines, to add more traffic, right, instead of degrading very fast. So what do we have here, right? Obviously, in production systems, in real life, Olivia wouldn't really implement this thing manually, right? She would probably use the existing solution for the infrastructure she builds. And some of those solutions include Envoy, very popular server-side, client-server communication framework. It has retry policies with retry budgets, gRPC as well, very popular framework, and Thrift, one of the things that we already touched on. So it also has a server part that and client part that sort of has this retries with the circuit breakers built in. So here comes the second lesson that we learned. Clients should be co-designed to handle overload. It's not enough to rely just on server. Basically, we should think about overload protection as the sufficient mechanism, holistic one that is applied to the entire stack, not only server alone, not only backend alone. It should be included in both client, like front end, backend, mobile apps, as well as backend. All right, we just have one more bit left to cover. So all clients are equal in terms of traffic. Olivia asked herself. What if single bad client can start sending too much requests? Can it potentially affect others? Here is the quick illustration. As usual, Olivia decided to load test and finds that if client C, for example, is misbehaving and sending too many requests, other clients are also impacted in that case. What does it mean? Right? Imagine we have availability of the system, right, broken down by client, and we have a time which is x-axis, right? And availability essentially is like out of all requests being sent by this particular client, what is the percentage of the request served successfully, right, within an appropriate time frame, meaning fast enough and successful, right? That we actually have what user expected from us. So 100 essentially means we serve everything, and 0 means we serve nothing. So, and in this case, Olivia finds out that, okay, single misbehaving client can actually cause all other clients to become unavailable. That doesn't sound right. So she decided to fix that problem. And solution to that one is by introducing quotas and rate limiting. So this is like a very broad topic on its own, and we can probably talk about that. It probably will take like another session to discuss, another webinar, another multiple hours to talk through it. But quick recap on this thing could be basically seen on this slide. So we want to make sure that every client, every user that uses our system is giving just a fair portion of the CPU time of the resource, and this is essentially what is called quota, right? Every user given a particular share of the system resources, and we want to make sure that if single user is overusing the quota, right, other users remain available. It doesn't impact everyone. So basically, we want to reduce the blast radius in case of the overload scenarios, like what we talk about in this presentation, right? And there are multiple ways to achieve that. One of the classic example and simplest one is essentially a token bucket algorithm. So, and this is what you can see on the slides. Essentially, imagine they have requests being sent to the server. They have this bucket of ephemeral tokens for every client in the system. And whenever a request arrives, we just fetch this bucket based on the client ID, right? And see, okay, every token in the bucket is basically something that we can take for the particular request. And if we have it, we can actually proceed with that. But if we don't, we cannot, right? So imagine you have 100 buckets in this, 100 tokens in this bucket. And then it basically means that you can process 100 requests, right? So once time goes, you add tokens to this bucket a little bit, right? So you add this to with the velocity so that you always have no more than, let's say, 100 tokens at any given second, in a way that you can only allow 100 requests at a particular second, at any given second to finish successfully. And everything that is above that, you basically reject. So Olivia decided to experiment with that approach, adding the quota, and she noticed that it actually helps dramatically reduce the impact, because now, even if client sees overusing the quota, if it's sending too much traffic, sure, the availability for that one will degrade, because most of the time it will start receiving rate limited exception, right, with limited error. But other clients don't care, because they can be served successfully without even knowing about this misbehaving client, right? Because we didn't give a chance to client C to consume all of the resources of our system. So the rest of the clients don't notice that. So there is an important detail here, right? Because how do we rate limit is really, it really depends on where we apply the rate limit itself, right? So it can be on the per user, but it can also be the global one. right? So in general, in the system, how many requests the system can handle and how many requests a particular customer can handle, can send, right? And we usually apply both. So popular solutions for that problem include Cloudflare rate limiting, Cloud Armor, AWS API Gateway have this rate limiting enabled. And this brings us to the third lesson that we touched on today. System not tested for overload is not overload ready. So there are so many scenarios that can lead to overload. It's impossible to basically think about all of them alone, right? So we definitely need to have an environment that is running the load test from time to time. And only if this load test succeeded, only if we can actually see that system handles a particular traffic growth, then we can say the system is overload ready. Otherwise, there is no way. All right, that was definitely like a brief and gentle intro to the topic. So I hope it was clear, and definitely waiting for your question.
Thank you very much for the webinar. I'm confident our audience took away a lot of valuable insights. So now we are moving into the Q&A session. And if you have any questions, please drop them into the chat box, please. And I see a lot of questions already, so we can start. The first question is from Roman. What signals should non-engineers look for the suggest overload is coming?
Yeah, that's a good question. So in general, non-engineers, they don't necessarily need to know about overload in general, because this signal won't be not actionable at the end of the day. But overload is one of the most popular triggers for the systems to misbehave and reliability. So I would suggest for non-engineers, the most important thing to look at is SLOs, right? How the system behaves, like what is the reliability and availability of the system. And this will include both overloads, bad releases, other types of issues, and then they can dive into the triggers of the SLO breaches whenever necessary.
Thank you. The next question from Ethan. Sergey, how do you test how do you test for overload scenarios if your system isn't even live yet?
Yeah, this is a good question as well. Well, you want to move fast generally, right? And people assume, sometimes I see this, that assume that if, for example, they skip this part of overload protection and just ship things to production, it will actually make things faster and improve time to market. But reality tells that if system is shipped without proper testing production, it's just a matter of time when you discover your users leaving you because of reliability breaches. So having some simple testing in place for overload scenarios is not that hard to implement, especially using modern cloud environments. And having the signal will give you a confidence in assessing, okay, do I have enough resources to serve the users or not, right? Can I actually provide the level of reliability that I want to users? Because ultimately what you care about is, are your users happier with the product that you have or not, right? And this is like a critical part of this question and critical part of the answer as well, right? So I would say shipping something simple before you even go live, worth it usually.
Okay, thank you very much. Next question is, what's the hardest decision you have had to make during an incident?
Yeah, good question. So I think quite a few, I cannot recall a particular one, but maybe like just one of them. I worked on a very large scale system, and it was an overload event actually. So the system got overloaded because of the misbehaving customers, like a set of customers. And the decision I made was to bring system back. There is only one way you can do that is to basically remove the trigger, right? And to remove the trigger means you need to remove the traffic, right? You need to remove those clients from your system. But those clients can be very important. They can be quite critical. But it might be just a few of them, right? That makes the rest of the clients suffer. So in that particular case, I decided to essentially bring back those, essentially bring down those critical clients, just a few of them, so the rest can actually benefit from that and recover. So this is not simple decision to make on its own, because you need to sacrifice like a higher earning client in the rest of much more higher in quantity but less earning clients. So this is interesting trade-off in general. So if you have a single one that brings you like a lot of dollars, and you have like a mini one that brings you just small amount, what do you choose, right? So this is sort of the dilemma that I faced.
Thank you for sharing your experience. So the next question is, can overload in one service really bring down an entire system?
Good question. All questions are good. So the short answer, it depends, because it depends on how the system is handling those cascading failures. In the first place, in a well-designed system, they should be very rare when a single. So in practice, it's possible, and happens all the time. And usually, like those incidents I showed you, like from the big companies, it's usually not a single mistake that caused the event. It's usually a combination of different things that lead to the disaster. And usually those things happen when there is a multiple triggers being involved and multiple, misses in the system. But if there is no overload protection, this is almost definitely guaranteed that a single misbehaving component in the system will bring the entire system down.
Thank you. We have one more question from Peter. What's your philosophy on moving fast versus staying safe?
Yeah. Well, moving fast, and I think this is one of the greatest misconception in general, that there is like sort of like a dilemma between moving fast and staying safe. In practice, it's actually you need to move fast to stay safe in a way. Like I won't probably dive into much of details, but you don't need to come up with a compromise in general, because if you don't move fast, when we say move fast, I mean like how often we ship the product features. So if you move fast and ship features more often, it usually means that you have a more mature infrastructure around that. How do you roll out these changes? How do you test them? It usually means that the process is more sophisticated and matured, which on its own reduce the likelihood of reliability breaches and safety concerns, right? Put a different way, you're motivated to build your systems around safety guidelines if you move fast. Otherwise, you won't be able to move fast, right? So it's not a dilemma, in my opinion.
Okay, thank you very much. And we have one more question. Can overload be caused by front-end issues too?
Well, interesting one. Yeah, so it can definitely, and as we discussed in the slides, it actually, clients, like front end as a client, it needs to be designed in a way it actually can handle those things. It actually should be co-designed with the server together to be able to protect us from overload. Recently, like just a month ago, like large company, Cloudflare, which is like a software infrastructure service provider, very popular one, faced this exact type of issue when they basically shipped a change in the front end that caused it to send much more requests than needed to the system. effectively causing a retry storm that we touched on quickly during the session, bringing the system down. So yes, that's very possible, very likely, and ever like large companies face it from time to time.
Okay, thank you. One more question. How do I know if my system is even overloadable yet?
Yeah, overloadable. Yeah, I never heard this this term before. It's quite nice. I guess any system is sort of like can be overloaded. In general, this is not specific to let's say like software systems. This topic in general. This is basically comes from the Q theory, which was long time back developed by and driven by telecommunication companies, and it introduced some like mathematical models for thinking about overload and traffic and those kind of things. And it basically sort of like described this pretty well in a way that, okay, what does it even mean for the system to be like above the capacity? So in general, any system can be above the capacity. So there is no such a thing as impossibility of overload. If we talk about like real production systems and real traffic, but there are some ways to protect the system from getting into that state, and those mechanisms and tools always evolving, right? This is a pretty much like dynamic area at the moment, and the problem is not solved. All right, I think we can move to the next one if you have any.
No, I think we have covered everything for now. Thank you very much for leading such interesting and engaging webinar for us. And I think feel free to connect with Sergey on LinkedIn to keep talking. And subscribe to the Top Voices newsletter and follow us on LinkedIn to stay updated on new events and expert talks. All links can be found in the description below. And thank you very much, Sergey. And thank you everyone for everyone who joined us today. And we hope to see you next time. Thank you very much.
Thank you. Thanks, Sophia.
Thank you. Bye-bye.